I'm going to spend a little bit of time talking about drawing Lewis structures for these molecules that feature atoms that violate the octet rule. So let's draw Lewis structures for SF6, BH3, and XeF4. When we're going about doing this, we're going to use the same exact process that we've seen previously. All of these cases, the central atom is going to be the first atom that's listed. We're going to put the skeleton, the outer atoms, we're going to make a skeleton, put lone pairs on the outer atoms, fill the inside, and we're going to try to follow the octet rule. Right? Based on, the title of this slide, we can assume that there's probably going to be some exceptions. But, we should generally try to get an octet on the central atom. Because that's generally going to correspond to something that is the most stable, but we're going to not necessarily be able to for various reasons here and need to make some adjustments. But otherwise, we want to follow the same pattern. Ideally, it's just not going to quite work out, but we want to follow it as closely until we have to break the octet rule. Sulfur hexafluoride, SF6. First, we get our valence electrons. That process is still the most important and hasn't changed. 48 valence electrons. Sulfur is going to be in the middle, and we connect out all of the fluorines. So you'll note right away that we have had to break the octet rule, because that sulfur currently has 12 electrons, because it has 6 bonds. So one of the things we want to check is this sulfur capable of having an expanded octet? And that's going to be based off its size. Sulfur is in period 3. That is after aluminum. It's only a couple after, but hey, it still counts. And so this can have an expanded octet. So sulfur is allowed to do this. It can have this. We can also see that this is really the only option because fluorine cannot have an expanded octet. So we really do need sulfur to have the expanded octet. It's going to sit in the middle here. So we've taken the 12 electrons in those bonds. We have 36 left after putting in all those single bonds. So we put lone pairs on all the outer atoms to fill the octet. Again, fluorine is in period 2A. It has to follow the octet rule. So it's in period 2, so we want to get it all of those. There's no electrons left. There's 6 outer atoms. They each have 6 electrons in lone pairs. That's 36. Subtract them out, we have 0 electrons left. So the question now when we ask ourselves, is this thing stable? All of the fluorines have lone octets, so they look good. The sulfur doesn't, but it's big enough to have an expanded octet, so that's good, but we should check its formal charge. Whenever you have an expanded octet or an unfilled valence, you always want to check the formal charge. We can see here sulfur has 6 electrons as an atomic valence because it's in column 6A. There's no lone pairs on this thing. There are the 12 electrons in the bonds. Subtract those out, we get 0. So this works out just fine. This is sulfur hexafluoride is actually it's not reactive, it's stable, it's unreactive. This is an expanded valence, but this molecule is very stable and it's very unreactive. It is happy to be here. One of the ways we can understand why this happens is sulfur, that idea of kind of sharing, breaking up those what were considered lone pairs on the atom. Sulfur has 6 valence electrons, and basically it just shares each of them in 1, 2, 3, 4, 5, 6 bonds. It's relatively big enough to do this. If you have lots of fluorine around, those fluorines really want to react and get into molecules. Sulfur can accommodate that, and so you can make sulfur hexafluoride. This is not a reactive gas. It is nice and stable, and with an expanded octet. Boron trihydride, BH3. Figure out the valence. Boron has 3. Each of the hydrogens has 1, 6 total. Boron's going to be in the middle. We also know that hydrogen can't be in the middle, so boron has to be in the middle. If we attach all those with single bonds, we're done. That's all the electrons. There is nothing else that you can put in there. That's going to be your Lewis structure for boron trihydride. That boron does not have a full octet, but there are also no more electrons to give it a full octet. It is stuck. It's not like you can even try to make a double bond or something. Those hydrogens can't form double bonds. So the octet isn't full. We should still check its formal charge. If you're going to violate the octet rule, make sure that the formal charges are 0. We can see with boron that it's boron. It tends to form just single bonds, 3 single bonds. So we can always kind of know, hey, that looks, it's wrong. It seems wrong in germ sense, but hey, that's boron there. It tends to form just the 3 bonds and no lone pairs. Xenon tetrafluoride. Xenon has 8 valence electrons. Each fluorine has 7, giving you 36. So on face, you can see something weird's going on. Xenon is a noble gas, right? Xenon already has 8 valence electrons. So xenon tends to not want to react. It doesn't do a lot of chemistry. Most of the noble gases do not do any chemistry. But xenon's down near the bottom. It's a little bit easier to get it to do something. You'll also note it's forming a molecule with fluorine, which is one of the most reactive elements. And so fluorine really wants those electrons. It is able to take some and force xenon to share some of its electrons. But xenon's in the middle. It's the only thing big enough to have an expanded valence. So it's going to go in the middle right here. And we connect out those lines to give to fluorine. So we've got that nice set up. So I've got 36 total electrons. I just put 8 down in the bonds. There's 28 left. I'm going to start by putting lone pairs on the outer atoms again. So I'll put them on the fluorine. They each have 6. So that's 24 electrons I just put there. There are 4 electrons left. We know that from the valence. If we kind of look at where they are, we have to put more lone pairs on something or bonds. But fluorine, if we remember, is in period 2. Fluorine cannot have an expanded valence. Only xenon is big enough. So these extra electrons need to be lone pairs on the xenon. We have 4 electrons. That gives us 2 lone pairs on the xenon atom. So the xenon gets 2 lone pairs. It forms 4 bonds then. That's an expanded valence. That is what, 2, 4, 6, 8, 10, 12 electrons around the xenon. So plenty of electrons around the xenon, definitely expanded valence. But if we look at the formal charge, we can see that it ends up with a formal charge of 0. Again, because xenon has 8 electrons. So it's as an atom, we can see that it has 2 right there that it's holding on to as lone pairs, 2 more. So it's 4 as lone pairs. And so as an atom, it had 4 more electrons. And we can see basically one of those went to share with the fluorine, one of those went to share with the fluorine, one of those went to share with fluorine, one of those went to share with another fluorine. And so you can make this molecule, right? And you can spread it out. And again, the reason why it forms, xenon as an atom is very stable, but fluorine as an element is very reactive. And so it is so reactive, it can overcome the resistance of xenon to reacting. So how you make these compounds is you just put tons and tons of fluorine in with xenon, crank up the temperature and really push it, really try to get that fluorine to react, and then you can make this pop out the other side. And so you can form these compounds. They're decently reactive, but they are stable. They don't fall apart, because falling apart would mean that you'd recreate fluorine atoms, which are not stable. And even fluorine molecules are very reactive. The xenon atom is happy to be by itself, but the reason is those fluorines really want to be inside molecules. They really want to share electrons, so they can drive that reactivity.